Alright, today we're talking about properties and applications of logarithms. So properties of logarithms, the change of base formula, and application of logarithmic functions. So the logarithmic product rule, we know that a log base a of a to the k equals k, and log base a of a to the n equals n, and log base a of a to the k plus n will equal k plus n. So in other words, basically, we undo the base a, we get the exponents added together, that means they're added overall. We also know that a to the k times a to the n is a to the k plus n. Using these allows us to compute log base a of a to the k times a to the n quantity equals log base a of a to the k plus n quantity equals k plus n. Log base a of a to the k quantity plus log base a of a to the n. This is an example of the general rule where we have log base a of x times y equals log base a of x plus log base a of y. Notice the multiplication on the inside of the logarithm has been converted to addition outside. So remember, logarithms are actually exponents. So since they're exponents, when you multiply on the inside, it's like adding them on the outside. The quotient rule. So we know that a to the k divided by a to the n equals a raised to the k minus n quantity. Using these allows us to compute log base a of a to the k divided by a to the n, that's in quantity inside my logarithm, equals log base a quantity a to the k minus n parentheses equals k minus n. The example of the general rule that log base a of x over y inside my logarithm equals log base a of x minus log base a of y. Notice that the division inside the logarithm has been converted to subtraction on the outside. So this is because of our negative exponent now. They could be think of as plus, minus, and if it was minus, you can move that negative one to the outside of your logarithm. We'll learn that rule in a second here with this logarithmic power rule. So we know that a to the k all raised to the r power is a equals a to the r times k power. Using this allows us to compute log base a, and so I have outer set of parentheses, and then I have an inner set of parentheses with a to the k in it, and then an inner set raised to r. That equals log base a of a to the r times k, so that's r times k, my exponent, inside my logarithm, and then I'm going to have that equals r times k. The example of the general rule of log base a of x to the r, that r can move out front as an exponent from an exponent now outside as a coefficient. So now I have r times log base a of x. Notice the exponential inside the logarithm has been converted to multiplication outside. So the summary of the logarithmic rules is we have log base a of x times y inside my logarithm equals log base a of x plus log base a of y. Log base a of x divided by y inside my logarithm equals log base a of x minus log base a of y. And log base a of x to the r inside my logarithm equals r times log base a of x. Every time we move from inside the logarithm to the outside, we are moving down one step on the order of operations. So this is parentheses, exponents, and then multiplication division. So our exponentials come down to multiplication division as coefficients up front. And then my multiplication and division can be thought of as being addition and subtraction. If I add or subtract inside the logarithm, there's no rule for that. So using the property of logarithms to expand each expression as much as possible, simplify any expression that can be evaluated without a calculator. So this is going to give me log base a of x, log base a of x times y divided by the square root of z. So I'm going to give everything its own logarithm. So this is going to be log base a of x plus, so anything in the numerator would be multiplied, so that's times log base a of y. And then if it's in the denominator, it'd be minus, so that's going to be minus log base a of the square root. I'm going to say z to the 1/2 power, which is the same thing as the square root of z. And then that's going to give me log to the base a. Now everything must be log base a of x plus log base a of y. And then I'm going to say minus. And the last step I need to do is I need to bring this exponential out as a coefficient up front in my logarithm. This is going to be 1/2 log base a of z. Next, for our next example, we're going to actually have, going to actually factor. There's nothing we can do on the inside right here because we're not multiplying or dividing. But if we change this right here, if we change it to, we factor out a 9. So I have 9. And that's going to give us, actually I think this is the example wrong. The more I look at it, the more I think this is wrong. I think this is supposed to be 3 right here. So let me change that example. This example makes more sense. So I'm going to factor out, so let me rewrite this as log base 3 of, and I'm going to have 27 minus 3x squared. So I'm going to change this 9 to 3. And so I'm going to factor that, and I'm going to factor it as log base 3. And on the inside, I'm going to pull out that 3. So I'm going to have 9 minus x squared. That's going to be log base 3 of 3 times 3 plus x and 3 minus x, because it's my difference of two perfect squares. So now I'm going to use my logarithm rule. I'm going to say log base 3 of 3 gets a separate x, its own logarithm. Log base 3 of 3 plus x gets its own logarithm. Remember, adding, subtracting, can't do anything with that. Plus log base 3 of, that's actually, I wrote that backwards up here. This is supposed to be 3 minus x. You don't see that? And this is supposed to be log base 3 of 3 minus x. And so now, one thing we want to do, if you can simplify an expression, it can be evaluated with a calculator. If you look at this term right here, this log base 3 of 3, we're going to rewrite that as 1. Because what did I raise 3 to get 3 to the first power? Raise it to the first power. So we'd ultimately write this final answer as 1 plus log base 3 of, and have 3 plus x, and then also I would have, run out of room, that's what I'm doing, plus log base 3 of 3 minus x. That's my AB. Now we look at the C. Once again, use the property to expand each expression as much as possible. Simplify any expression that can be evaluated without a calculator. So this is the natural log. So once again, the easiest way to do this is to say we're going to have the natural log of 6x divided by 5, and then the third root of e to the fourth, all inside my natural logarithm. So I'm going to say the natural log of what's in the numerator, so this is going to be 6 plus the natural log of x, and then anything in the denominator gets a negative sign, so it's going to be minus the natural log of 5 minus the natural log of e. And I'm going to say that's to the 4/3. I'm going to move that 3 as a root, a third root of e to the fourth, and express that as e to the 4/3. Once again, if you can simplify anything without a calculator, do that. So we're going to get the equal to the natural log of 6 plus the natural log of x minus natural log 5. Can't evaluate any of those. It doesn't make any sense. But this one, what did I raise e to get e to the 3/4? I raised it, 4/3. I raised it to the 4/3 power. Alright. Next, you need to use the properties of logarithm to rewrite each expression as a single logarithm with a coefficient 1. All exponentials should be positive. So basically, we're going to condense anything. If there was a coefficient out front, we'd move it in as an exponent first. So if we condense these, if there was something like out front, like there's a 1 understood here, we'd move it as 1 here. But it's understood as a 1, so it really doesn't need to be bothered with. But here, all we need to do is condense this. Anything with positive signs end up in the numerator. Anything with negatives end up in the denominator. So we just simply rewrite this as log base 5 of A times B, all divided by C. That's inside my log base 5. Here are two ways we can do this. B, we have 3 times the natural log. Inside my natural log, I have the third root of e to the fourth again. And then I close out those parentheses, minus the natural log of x times y inside my logarithm. And all the 3's times all that quantity. So we could bring that 3 in first and deal with it that way, or we could wait till later. I'm just going to bring it in to get rid of my parentheses. I have the natural log of, and I'm just going to raise this e to the 4/3 instead of using that cube root, minus 3 natural log of x times y inside my logarithm. And so that's going to get me, I'll move that 3 inside, so I'm going to have that natural, so this 3 comes inside as a coefficient, it's outside as a coefficient, I'm going to use it as an exponent. So here I'm going to get the natural log of e to the 4/3 times 3 in my exponent, and then we'll say minus natural log of x to the third, y to the third. Remember that 3 belongs to both those terms. If we raise the whole thing to the third power, then we're going to get x to the third, y to the third. And then since it's minus, it's going to end up in the denominator. And when we combine this, and we're going to say the natural log of, and then I'm going to say e, and it was raised to the 4/3 times 3, so that would just be e to the fourth all over x to the third, y to the third. What we have here. So looking at this, I know there's some temptation to evaluate the natural log halfway through the problem. And looking at that, you're like, oh, wait, I want to convert it all to one logarithm single expression. So I don't want to evaluate the log until I'm at the very end, or what's inside my logarithm at the very end. And if it does simplify at the very end, do it. Here in this case, that's not going to simplify any unless I take it apart again first. And that would defeat the point of condensing it. Do it again here. And so now we're going to basically, once again, we're going to have log base 5 of x minus 4 minus the log base 5 of x minus log base 5 of 9. So that's going to give me, on the inside of my log base 5, I'm going to have x minus 4 in the numerator. And then I'm going to have my negative logarithms. Those end up in the denominator. So that log base 5 of x, or that negative log base 5 of x, and negative log base 5 of 9 end up in my denominator. The x and the 9, respectively, end up in the denominator. And if it simplifies inside here, like if you just have a simple multiplication Hawks to do, just multiply that out. But if you don't, just leave it alone. So that doesn't simplify. So I have, my final answer is log base 5 of x minus 4 all over 9x inside my logarithm. Most scientific calculators only have base e and base 10, but we often want to evaluate a logarithm with a different base. We know that log base 2 of 7 must be between 2 and 3, because 7 is between 4 and 8. For a more precise answer, we use the change of base formula. Log base a of x equals log base b of x over log base b of a. For a calculator evaluation, b would be either 10 or e. Some calculators can do any base you want. Note that x, a, and b must all be positive, and a and b cannot be equal to 1. So you have a calculator here. It has right here, it has your natural log. Oops, focus. Oh, it wants to focus in on, okay. You have your natural log here button. Oh, come on. Never wants to. Your natural log here and your log here. So using a change of base formula, evaluate to 4 decimal places. So we're going to say log base 7 of 100. If you type that in your calculator and say log of 100, it'll tell you 2, because that's automatically log base 10. So we're going to change this to log base 10. So we're going to have, always try to change it to base. So here I'm dealing with 100. So log base 10 would make perfect sense to use. So I change it to log base 10 of 100, just log of 100 over log of 7. So that would give me log of 100 is 2 over log 7. So we can punch that into our calculator. And so we're going to have 2 divided by log 7. That would be 23665. Approximately 2.366. And that'd be 6 again. And 4 decimal places. Next we have log base 1/3 of 14. So I change that. Let's just do natural log. So natural log of 14 over natural log of 1/3. And so that, just look at that on our calculator. So here's where you need to make sure. You probably can get away on fancy calculators like this without using an excessive amount of parentheses because they're pretty smart. But let's just use parentheses, at least an even number of them. Or close out my parentheses, divide the whole thing by. We have natural log of, it's going to be 1 divided by, come on. That seems about right. It should be a negative number because the 1/3 base is smaller than the 14, or it's less than 1, so taking the reciprocal of that would give me a number larger. So that seems about right. And if you always want to make sure you did it right, this is supposed to be 2. You want to make sure you always did it right, so you can always take your number and say, I'm going to raise this number. So you say, I'm going to take 1/3, so divide by 1/3, or sorry, not answer. Say 1/3, and I'm going to raise that 1/3. If it would stay focused, that would be so nice. Focus. It literally just changes every 5 seconds. See, these cameras autofocus on what they think is important, and so they don't stay focused, even if I have autofocus off. And then I'm going to raise that to the answer. Just whatever. Second function answer. And then I'm going to hit enter, and I get 14 back out. So just take your base to your answer right here, just to double check, and you should get this number inside back out. Just to double check it. Alright, so application of logarithms. So in chemistry, the pH of solution is defined as the pH equals the negative logarithm of H3O plus, where H3O plus is the hydronium ion concentration moles per liter in the solution. Solutions with a pH of less than 7 is to be acidic, while those with pH greater than 7 is said to be basic. And there are there are acids that go to like the zeros, and there are basics that go well above 14. But for us in everyday life, we try to stick around the 7s. You can go as low as 3, and after that it starts getting painful. If you spill some on your hands, you can go up to 10, and then after that it starts to get crazy. For basics, you wouldn't want to put that on your skin. So with this in mind, we use pH. And so if we say find the pH solution with a hydronium ion concentration of 5.72 times 10 to the negative 4th hydronium ion concentration, all you got to do is say the negative log of H3O plus is going to equal the negative log of your H3O plus hydronium ion concentration, which is going to be 5.72 times 10 to the negative 4th. And since you have calculators, you have scientific calculators, you can just plug this into your calculators as is. Come on, focus. You're determined not to focus for me, I can tell. Whenever the camera's not on, it focuses fine on my screen. And so you just say negative, and then you say log of, and then you're just going to put in 5.72. That's going to be times 10 raised to the negative fourth. Oops, let me close up that. Delete. Over. Alright, so that's going to give me 3.246. Now, you only go to as many significant digits as you're given, so basically you'd stop. You're given 3 significant digits, and you go 3 significant digits here. If you wanted to look this out a little bit long way, what we were taught to do way back in the day is to use our logarithmic rules to break this up into 2 logarithms. And we get negative log of 5.72, and that would be now plus 4. So basically we took this 10 to the negative fourth and changed that to a 4, because we're multiplying the inside, we add 4 on the outside, and so we have the negative of log of 5.72, which would be a number, it'll be number less than 1, and so it'll be about 0.7 or something, and then you subtract that from 4, negative 0.7, and you get this answer right here, 3.42. And that's it. So that's your pH of that solution. Once again, what logarithms are really used for, and people think logarithmically, it's how people naturally think. A lot of times people, when they're dealing with large numbers, don't actually understand what the number means. They just count the number of zeros. So if you had something between 0 and a trillion, right, which is 9 to the 10th power. No, that's a billion. A trillion is to the 12th power. 10 to the 12th power. And you said, where's a billion? A lot of people would mark a billion about right here where 10 to the 9th would be if this was a number scale from 0 to 12. But that's not where a billion is out of a trillion. A billion right here, 10 to the 9th is all the way down here. So in other words, in your mind, you're not counting, you're not actually understanding what's going on. You're just counting the number of zeros, and you're saying, if this has 12 zeros, if a trillion has 12 zeros, then obviously 10 to the 9th would be, 3/4 of the way up, something like that. No, it's down here right at 0, because a billion is 1,000 times smaller than a trillion. It takes 1,000 billions to make 1 trillion. And if I broke this up into 1,000 pieces, that each one of those pieces is a billion out of a trillion. So a lot of people lose track of that. So it's easier for the mind to deal with small numbers under 20. After you get over 20 more digits than you have on your body, after you get over 20, your mind starts to lose track of things. And then once you're past like the hundreds, your mind just kind of glazes over and just counts the number of digits. And you just keep track of things that way. So things that deal with really large or small amounts like hydronium ion concentrations, or large amounts like earthquakes, Richter scale, you turn those down into single digits or double digit numbers. So they're a lot easier to understand. Decibels are that way as well. But yeah, so logarithmic scale is how your brain normally interprets digits and things. The actual number representation. So we turn it to logarithms to help our brain understand it. And it makes math easier too when we're going down one change, and we take exponents, and that converts to multiplication, division converts to addition, subtraction. It makes things easier in that respect, because some things would be impossibly hard. Especially back in the day when we didn't have calculators and we had to look up everything on logarithm tables. But you all have calculators now, so yay for progress. You all have a great day.